I will explain about common source amplifiers. The definition of common source amplifier: common source amplifiers with resistive load, common source amplifiers with MOS diode connected load. Definition: in common source amplifiers, source node is common between the input and the output. That is, input, that is Vin, is referred with respect to the source, and output voltage Vout is referred with respect to the source. Here the source potential is at a constant potential. Common source amplifier with resistive load. So we have an NMOS and its gate is provided with UN, source is connected to ground, output is taken at the drain of the NMOS, and we connect a load, that is a resistive load, between the drain and UDD. This is nothing but an inverting amplifier which has a negative gain. That is, the bias point is set by the resistor transfer function and the NMOS transfer function, that is by R and VGS. The output voltage Uout is given by UDD minus ID times R. ID is defined by the bias point at which the NMOS is operated. That is ID equals to beta y2 into UN minus UTH the whole square. The bias is done in such a way that Uout is at UDD y2, so that we have a good input and output swing. This is explained in detail in Microelectronics4a inverting amplifiers video. Let us find the gain of the inverting amplifier by using the small signal model approach. Draw the small signal model of the common source amplifier with resistive load. So it consists of gate, which is connected to UN, source connected to ground, which is given here, gate, UN, source connected to ground. In small signal model analysis, we connect the DC voltage sources to ground, that is UDD is connected to ground. We have drain D1 and the current is given by GM1 times UN. We have RDS1 between the drain and source, and we have R connected between the drain and the ground, since UDD is grounded. So R comes between Uout and ground as shown here. To find the intrinsic gain, that is the gain at low frequencies, we have to find minus GM times R out of the circuit. Gain is always given by minus GM times R out. That is the intrinsic gain. Here the gain is calculated at low frequencies, that is S tending to 0. So effect of capacitors, that is whose impedance is given by 1 by SC. So when S is at 0, Z is at infinity, which means we can open circuit all the capacitors when calculating the intrinsic gain. Let us find GM. You know, GM is nothing but I out by UN when Uout equals to 0. So in the small signal model, set Uout to 0, that is short Uout to ground. When Uout is shorted to ground, R and RDS1 get shorted. However, the voltage control current source remains, and whose value is given by GM1 times UN. So the I out current is nothing but GM1 times UN. So I out equals to GM1 times UN. I out by UN is nothing but GM1. So we get gm to be equal to gm1 here. Let us find r out. R out is nothing but u out by I out when u in equals to 0. So short u in to ground, which means UGS1 equals to 0 or u in equals to 0. So the voltage controlled current source becomes open. Now we have u out which equals to I out times R parallel RDS1. So we can say that u out by I out which equals to R out equals to R parallel RDS1. So the gain of the common source amplifier with resistive load is given by minus gm R out, which equals to minus gm1 times R parallel RDS1. The value of R is generally small compared to the RDS1 of the NMOS. For example, R will be in the range of 100 kilo ohm and RDS1 will be in the range of 10 mega ohms. So when you parallel R and RDS1, R wins. This is because R parallel RDS1 is nothing but R into RDS1 divided by R plus RDS1. Here we can say that R plus RDS1 is approximately equal to RDS1 since R is very small compared to RDS1. So here I can say R into RDS1 divided by RDS1. So cancelling this, R parallel RDS1 can be approximated to be equal to R. So the gain of the inverting amplifier or the common source amplifier with resistive load is given by minus gm1 times R. Gain using direct approach using small signal analysis. The gain can be found out using the small signal analysis by direct approach. That is, in the small signal model, we know that by applying KCL at node D1, we can say that current, that is GM1 times UN plus I1, that is current through RDS1, plus I2, that is current through R, equals to 0. Here I out is equal to 0, means this current will be equal to 0. So substituting I1 to be equal to U out by RDS1 and I2 to be equal to U out by R, we can write U out by RDS1 plus U out by R plus GM1 times UN equals to 0. Now we can write GM1 times UN equals to minus U out into 1 by R plus 1 by RDS1. Therefore, U out by UN equals to minus GM1 times R parallel RDS1. So R parallel RDS1 can be approximated to be equal to R when R is very less compared to RDS1. So gain is given by minus GM1 times R. Input voltage swing Vn. Here the range of input voltage swing, that is Vn, is that Vn should be greater than Vth, and Vn maximum value should be high, and it should not result in the transistor going to the triode region. The output voltage swing of the common source amplifier here is given by U out max, has no limitation. U out min, that is U out cannot go to ground. We want the transistor T1 to be in saturation. The condition for saturation is VDS should be greater than or equal to VGS1 minus VTH. So U out has to be greater than VGS1 minus VTH. So V out should be greater than Vin minus VTH. This term is nothing but VGS1 effective. So U out has to be always greater than VGS1 effective.